14 million years ago, our solar system drifted directly through a hidden river of gas stretching 9,000 light-years across the galaxy. Nothing alive then could have felt it happening. Yet scientists now believe the timing lines up almost exactly with one of the most dramatic climate shifts in Earth's ancient past, a sudden expansion of ice at the bottom of the world. Using data from a spacecraft that has mapped over 1 billion stars, researchers recently retraced our solar system's exact path through the Milky Way, and what they found waiting in that wreckage of deep time is still reshaping how scientists understand our planet's own climate history. Tonight we follow that trail, back through the gas, back through the ice, to a discovery that is still unfolding. If wandering through quiet corners of deep time like this helps you drift off, liking and subscribing helps this channel grow more than you know. For now, just settle in and get comfortable. In 3, 2, 1, liftoff. There is a kind of stillness that settles over a place late at night. The porch light goes out, the road goes quiet, and for a while it feels as though nothing in the world is moving at all. Look up on a clear night, away from the glow of any town, and the stars themselves seem to agree with that feeling. They hang there, fixed, patient, exactly where they were the night before, and the night before that, and the night before that. It is one of the oldest and gentlest illusions the sky has ever offered anyone who has stood beneath it, and it happens to be completely wrong. Your chair is moving right now, and so is the ground beneath it. Earth spins on its axis at roughly 1,000 miles an hour at the equator, and it circles the sun at nearly 67,000 miles an hour, a full trip made once a year, without ever once arriving early or late. You do not feel any of this for the same reason a person does not feel the smooth, steady motion of a train gliding along a straight, level track. There is nothing to push against, no jolt, no resistance, only constant, silent movement, invisible to anyone riding quietly along inside it. Most people learn the basic facts of it in school and file them away as settled, one of those pieces of childhood science tucked into memory alongside state capitals and multiplication tables. It took human beings a remarkably long time to accept even that much motion. For most of recorded history, nearly every culture assumed the ground beneath their feet was the one fixed point in all of creation, with the sun and stars doing the moving around it. It was not until the 16th century that a Polish astronomer named Nicolaus Copernicus argued, carefully and at some real personal risk, that the opposite was true, that Earth itself was the one in motion, circling a sun that only appeared to rise and set. The idea took generations to be fully accepted, and it reshaped how people understood their own place in creation. And yet, even Copernicus, working out his careful diagrams by candlelight, had no way of knowing about a third motion, one far larger and far slower than anything he was describing, a motion that would remain completely invisible to human observation for another 400 years. The entire solar system, the sun and Earth and moon and every planet riding along with it, is also moving, carried in a long, slow orbit around the very center of the Milky Way galaxy. Earth's yearly lap around the sun is a modest errand by comparison. This is a genuine voyage, one that carries our whole star system through the depths of the galaxy at a speed of roughly 130 miles every single second, well over 400,000 miles an hour. And yet, because the distances involved are so vast, that same tremendous speed only carries the solar system once around the galactic center every 225 million to 250 million years or so. To put a number like that in perspective, Consider what Earth looked like the last time the solar system was anywhere near this same position along its long galactic circuit. There were no flowering plants anywhere on the planet. The very first dinosaurs were only just beginning to appear, small and unremarkable creatures with no idea what they would eventually become. Entire species that would one day dominate the planet, walk across open ground, build fires, and look up at this very same sky, had not yet been born, and would not be born for tens of millions of years still to come. The continents themselves were still fused together in one great connected mass, long before anything like the Rockies or the Alps had begun to rise. Even the stars overhead would have looked unfamiliar, arranged into different patterns entirely, since the stars themselves are forever drifting along their own slow, private paths through the galaxy. We are, all of us, riding on a carousel so large and so slow that our own star has completed something like only 20 full turns of it since the sun itself first came into being. Roughly 4.5 billion years ago, 20 turns. And here we are, on turn number 20, catching our breath for a moment before the story continues. It is tempting to picture outer space as one uniform kind of nothing, a black backdrop with stars scattered across it like salt thrown across a dark tablecloth. But the space between the stars is not uniform at all, and it is far from empty. Some regions really are close to a perfect vacuum, holding only a stray atom or two in a volume of space the size of a house. Other regions are thick with gas and fine dust, cold and quiet places where the raw material for new stars slowly gathers and collapses under its own weight. Astronomers even have names for how these denser clouds appear. When a nearby young star bathes its surrounding gas in enough radiation to make it glow on its own, the result is called an emission nebula, glowing pink or red in most photographs because of how hydrogen gas lights up under that kind of energy. When a cloud simply blocks the light of whatever lies behind it, with no glow of its own, it shows up instead as a dark, star-blotting silhouette. Both are really the same basic material, gas and fine dust drifting through the space between stars, looking different only because of what happens to be lighting them or not lighting them from any given angle. That gas is mostly hydrogen, the simplest and most abundant element in the universe, laced through with a smaller amount of helium and a fine dusting of heavier elements forged long ago inside older, long-dead stars. It is, in a very real sense, the same raw material the sun itself was built from, roughly 4.5 billion years ago, inside a cloud that has long since been used up, scattered, or blown away by the very stars it helped create. Left alone, a cloud like this can drift for millions of years, cold and quiet, doing very little at all. But given enough time and the right gravitational nudge, dense pockets within it begin to collapse inward under their own weight, slowly at first, then faster, heating up as they shrink, until finally, at the very center of that collapse, a new star flickers to life. Every star visible in the night sky, including the sun itself, was born this same way. As the solar system makes its slow circuit around the galaxy, it does not pass through the same kind of neighborhood the whole way around. It drifts from sparse regions into denser ones and back again, the way a ship might sail out of open ocean into a low bank of fog and out the other side again, with none of the passengers ever feeling a thing change beneath their feet. For most of the history of astronomy, nobody could say with any real confidence what that near neighborhood actually looked like. You might expect the region closest to our own sun, the very patch of galaxy we are sitting in, to be the easiest one of all to chart. In practice, It turned out to be one of the hardest puzzles in the entire field, and the reason is almost embarrassingly simple. We are standing inside it. For centuries, the fundamental challenge of astronomy was never really about seeing things. Even ancient observers, working with nothing more than their own eyes, could plot the position of a star against the background sky with real precision. The far harder problem was always distance. Position tells you which direction to look. Distance tells you what you are actually looking at. The one method available to earlier astronomers, a technique called parallax, works something like closing one eye and then the other while holding up a finger, watching how it seems to shift against the background behind it. Astronomers use the same basic trick on a much larger scale, comparing a star's position from opposite sides of Earth's orbit around the Sun, 6 months apart, to work out its distance from that tiny shift. The technique works beautifully for the nearest stars. Push it out much farther than a few hundred light years, though, and the shift becomes too small for even the most careful instruments to measure with any real confidence, and the whole method quietly breaks down. Imagine trying to draw an accurate map of a forest while standing among the trees, with nothing to guide you but a small notebook recording the rough direction toward whichever trunks happen to be visible from wherever you happen to be standing. That was roughly the position astronomers found themselves in whenever they tried to study the gas and star clusters nearest the Sun. An outside observer looking down on our galaxy from some great distance might take in the whole pattern in a single glance, the way a person flying overhead in an airplane can see the true shape of a forest that looks like nothing but scattered trees from the ground below. From inside, surrounded by dust and gas that block long lines of sight in nearly every direction, the true shape of our own neighborhood stayed hidden for generation after generation of careful, patient astronomers. For more than 100 years, the leading picture was of a loose, ring-shaped band of young stars and star-forming clouds circling near the Sun, an idea that dated back to observations made in the 1870s by the American astronomer Benjamin Gould, and came to be known informally as the Gould Belt. It was a reasonable guess, built from the best tools available at the time, and it was taught, more or less unchanged, for generation after generation of astronomy students. It was also, as it would eventually turn out, not quite right. What finally broke the puzzle open was not a new telescope pointed outward, but a new way of measuring distance itself. In 2013, the European Space Agency launched a spacecraft named Gaia, sent not to photograph any single object in dramatic close-up, but to sit at a stable point in space, known as the second Lagrange point, nearly 1 million miles beyond Earth, far enough away to avoid our planet's own light and shadow, and measure the precise position, distance, and motion of more than 1 billion stars, one after another, year after year, with a patience and a precision no human observer could ever hope to match. From that quiet vantage point, the spacecraft has spent well over a decade slowly spinning and scanning the entire sky again and again, building up its measurements one careful pass at a time, the same patient, repetitive work of a lighthouse keeper logging every ship that passes night after night for years on end. Where earlier generations of astronomers might confidently measure the distance to a few thousand of the very nearest stars, Gaia was built to measure well over 1 billion of them, using the same basic principle behind ordinary parallax, only now applied with a precision earlier astronomers could only have dreamed of. That flood of precise distance measurements gave astronomers something they had never really had before: a true three-dimensional map of the space around the Sun, built out of real distances rather than the flattened, two-dimensional impression the night sky ordinarily offers. And it was in the middle of working with exactly that kind of data that an astronomer named João Alves stumbled onto something nobody in his field expected to find. Alves is a professor of stellar astrophysics at the University of Vienna in Austria, the kind of scientist who has spent an entire career studying how clouds of gas and dust collapse under their own gravity to form new stars. During the 2018 to 2019 academic year, he took up a fellowship at the Radcliffe Institute for Advanced Study, part of Harvard University, with a fairly modest goal in mind: to build a better three-dimensional map of the star-forming clouds nearest to our own Sun using the fresh Gaia measurements, together with a technique known as three-dimensional dust mapping. The idea behind that technique is simpler than it sounds. Starlight passing through a cloud of interstellar dust gets dimmed and subtly reddened in much the same way sunlight passing through smoke or haze looks dimmer and redder near the horizon. By carefully measuring exactly how much dimming and reddening shows up in the light of many thousands of individual stars, and combining that with Gaia's precise distance measurements for those same stars, researchers can work out not just where a cloud of dust sits in the sky, but how far away it actually is, and how thick it really is. Processing a dataset of that size was itself no small task. Alves and his colleagues were not simply studying a handful of interesting stars. They were sifting through the positions and distances of many thousands of individual stars and clouds, all at once, using statistical techniques that had barely existed a decade earlier, hunting for a pattern buried in a fog of ordinary-looking numbers, the kind of work that rarely makes for dramatic photographs. Mostly quiet hours spent in front of a computer screen, rather than long nights spent hunched over a telescope eyepiece. Working alongside colleagues at Harvard, including the astronomer Alyssa Goodman and a graduate student named Catherine Zucker, Alves began plotting the true distance to cloud after cloud, region after region, expecting, if anything, to end up more or less confirming the old, familiar picture of that loose ring of stars. What the data showed him instead was strange enough that, by every account, it took the team real time simply to trust what they were looking at. Modern astronomy often works this way now. Less a single dramatic night spent squinting through an eyepiece, and more a long, patient process of building a three-dimensional model on a computer screen, then rotating it, testing it, and rotating it again, looking for a pattern the human eye might otherwise miss, entirely in a flood of numbers. Somewhere in the middle of that process, looking at their new model from just the right angle, the shape of what they had actually built finally became impossible to unsee. Rather than a ring, the data traced out something closer to a single, long, gently undulating filament, rising above the flat plane of the galaxy in one place, dipping below it in another, then rising again. Like a ripple sent rolling down the length of a rope, someone has given a single sharp shake. It ran for a genuinely staggering distance, and it was, by a wide margin, the single largest coherent structure of gas ever mapped anywhere in our part of the galaxy. The team checked their numbers again. They checked them a third time, and then a fourth. The way any careful scientist checks a result too strange to trust on the first look. The shape held every time. What earlier generations of astronomers had mistaken for a loose, scattered ring, viewed only from the inside and flattened by the limits of older, cruder measurements, was in fact one single, continuous, wave-shaped structure, and the solar system sat almost directly beside it, closer than anyone had ever imagined. The team published their discovery in the journal Nature on the 7th of January, 2020, and they gave the newly revealed structure a name to match the place where the work had come together: the Radcliffe Wave, in honor of the Radcliffe Institute itself, and, in a quieter way, in honor of the generations of women astronomers historically associated with Radcliffe College who had helped build the field long before it welcomed them as equals. Goodman would later describe the team's own reaction as something close to disbelief, admitting that no one in the field had genuinely expected to find a giant, wave-shaped river of gas sitting almost directly beside the Sun. This was not some faint smudge at the far, unreachable edge of the galaxy. It was practically in our own cosmic backyard, and it had been sitting there, unnoticed, the entire time anyone had ever thought to look up. The Radcliffe Wave was hardly the only secret that same flood of Gaia data would eventually help reveal. In the years since the spacecraft's launch, the same basic three-dimensional approach has helped astronomers trace the tattered remains of smaller galaxies that collided with our own in the ancient past, and map rivers of individual stars torn loose from disrupted star clusters, streams of stars entirely distinct from clouds of gas like the one at the center of tonight's story, yet part of the same larger flood of discoveries. Gaia helped reconstruct the Milky Way's history in a level of detail that would have seemed like pure fantasy to earlier generations of astronomers, working only from flat, two-dimensional photographs of the sky. But of everything that mission would eventually uncover, few discoveries sat as close to home or felt quite as personal as the realization that an enormous structure of gas had been curling through our own galactic backyard the entire time. News of the discovery spread quickly through the astronomical community. At scientific conferences held in the months that followed, the Radcliffe Wave became one of the most talked about findings in the entire field, discussed and debated by researchers who had spent entire careers studying this same patch of sky without ever suspecting what it actually contained. Follow-up studies soon began arriving from research groups around the world, each one testing the new picture against its own data, each one finding the same underlying shape, no matter which angle it approached the problem from. The discovery did more than add one new structure to the map. It forced astronomers to reconsider the very architecture of the galaxy's local arm, the modest spiral arm of the Milky Way that happens to contain our own Sun. For years, that arm had been treated as a fairly minor, unremarkable feature, a small spur compared to the galaxy's grander spiral structure. The Radcliffe Wave suggested something different, that the local arm might be better understood not as a simple spur at all, but as one visible piece of this long, undulating structure, a single connected feature stretching much farther than anyone had previously drawn it. The map of our own galactic neighborhood, something astronomers had long considered largely settled business, suddenly needed to be redrawn. Understanding a structure like this matters for more than mere cartography. Too, the clouds threaded along the Radcliffe Wave are still actively forming new stars today, which means the wave is not simply a leftover feature from the galaxy's distant past. It is a living nursery, continuously seeding the local arm with new suns and new planetary systems, one gently glowing patch of sky at a time. To understand what Alves and his colleagues had actually found, it helps to picture the scale involved. The Radcliffe Wave, as it came to be called, stretches for something close to 9,000 light-years, a single connected structure of gas, roughly 20 times longer than it is wide, curling gently up and down, across more than 500 light-years above and below the flat disk of the galaxy. The way a long ribbon left hanging on a clothesline will rise and fall in a light, steady breeze. Picture the entire Milky Way galaxy shrunk down small enough to rest on a dinner table. At that scale, the sun and every planet riding along with it would be a single grain of pepper resting near the table's edge, and this one ribbon of gas would still stretch across nearly a tenth of the whole table, an enormous, winding feature laid across an already enormous canvas. All told, the wave holds more than 3 million times the mass of the sun, locked up almost entirely in gas and fine dust rather than finished, shining stars, and colder in its densest pockets than 400 degrees below 0 Fahrenheit, far colder than any winter ever recorded anywhere on our own planet. To stand inside a cloud like that, if such a thing were even possible, would mean standing in a near-total vacuum by any ordinary earthly standard, thinner by far than the finest vacuum ever created in a laboratory, and yet, on the scale of interstellar space, astonishingly crowded compared to the emptiness surrounding it on every side. Woven into that great ribbon of gas are some of the most famous stellar nurseries in the entire night sky, regions any long-time stargazer might already recognize by name, even without knowing they were ever connected to one another. The Orion complex is there, the glowing stellar nursery behind the middle star of Orion's belt that has been visible to the naked eye on any clear winter night for as long as human beings have been looking up. So are the star-forming clouds of Taurus, marked by the bright, close-knit cluster of stars known as the Pleiades, easily visible without any telescope at all on a dark night. So are the clouds of Perseus, easily found near the famous meteor shower that borrows its name from the very same patch of sky, along with the clouds of Cepheus and Cygnus, the swan-shaped constellation whose outstretched wing points toward one of the richest star-forming regions visible anywhere in the northern hemisphere. Each one has been a familiar landmark to generations of amateur astronomers with a backyard telescope and a star chart. Each one, it turns out, is simply a single bright bead threaded along the same immense, curling strand of gas. There is something quietly humbling in that fact, easy to overlook at first. Professional astronomers, backyard hobbyists, and casual stargazers alike had been studying every one of those famous clouds separately for the better part of 2 centuries, naming them, cataloging them, photographing them in ever finer detail, all without ever suspecting they were simply looking at different stretches of the very same river of gas. It took a spacecraft built to measure the positions of over 1 billion stars and years of patient calculation to finally step back far enough to see the whole shape at once, hiding in plain sight along the whole length of the sky. The story did not end with the wave's discovery. 4 years later, in 2024, a follow-up study led by a Harvard researcher named Ralph Konietzka returned to the very same data with an even more precise question in mind. Was the Radcliffe Wave simply shaped like a wave, frozen permanently, in that form the way a ribbon might be pinned in place along a wall? Or was it actually moving like one, rising and falling over time the way a real wave rolls steadily across open water? By carefully tracking the motion of young star clusters scattered along its length, watching how their positions shifted ever so slightly year after year, the team found their answer. The Radcliffe Wave is not merely wave-shaped. It is genuinely oscillating, swelling upward and sinking downward across the plane of the galaxy in a slow, rolling motion, its star clusters bobbing gently as they ride along with it. The way corks bob on the surface of a pond long after the stone that disturbed it has sunk out of sight. Nobody is entirely certain yet what first set a structure this size oscillating in the first place. The leading idea connects it to the same gravitational forces that shape the galaxy's spiral arms. The slow, grinding tug of the Milky Way's own rotation, acting on a long filament of gas, the way wind acts on a flag, only stretched out over millions of years instead of seconds. Something that had already seemed like one of the strangest structures ever mapped in our part of the galaxy turned out to be something closer to a living, breathing feature of the Milky Way itself, a wave in every sense of the word, not only in shape, but in motion. And that second discovery, more than anything else, is what makes the next question so difficult to set aside. If the Radcliffe Wave is real, if it is genuinely enormous, genuinely nearby, and genuinely in motion, rising and falling across the disk of the galaxy over long stretches of time, then the solar system's own slow, patient orbit raises an obvious possibility. Both are moving. Both have been moving for a very long time, on paths shaped by gravity rather than by any plan. Somewhere in that long, quiet dance between a star and a structure of drifting gas, is it possible that the two of them ever actually crossed paths? That the Sun and the Earth riding along beside it once passed directly through that cold, dense ribbon of gas, rather than simply orbiting somewhere nearby and admiring it from a comfortable distance? Answering a question like that is never as simple as it sounds. It means reconstructing with real precision exactly where the Sun has traveled across millions of years of galactic history, then checking that reconstructed path against the wave's own position at every step along the way. A little like determining whether two old hiking trails, each mapped only in rough, incomplete sketches, ever actually crossed each other deep in the same forest, using nothing but each trail's general direction and pace to work backward toward an answer. The tools required to even attempt an answer, precise stellar motions traced back across tens of millions of years, only became available in the years immediately following the wave's own discovery, which meant that for a while, even the scientists who had found the Radcliffe Wave in the first place had no way of knowing whether the Sun itself had ever brushed against their own discovery. For a while, that question remained open, filed away alongside every other loose thread the discovery had left behind. It would take a second piece of research, one built specifically to go looking for an answer, to find out how close that ancient encounter might actually have come, and when, if it ever happened at all, it might have taken place. For years, that question waited. It is one thing to prove that an ancient structure of gas exists somewhere out in the galaxy. It is an entirely different and far harder thing to prove that a specific star, moving along a specific path for millions of years, actually passed through it. Doing that meant reconstructing not just where the Radcliffe Wave sits today, but where it used to sit, drifting through the galaxy over millions of years into the past, and doing the very same thing for the Sun, then checking whether those two separately reconstructed paths ever actually lined up. Neither path could simply be read off a single observation. Both had to be built painstakingly out of thousands of individual measurements, each one carrying its own small uncertainties that could easily compound into a hopelessly blurry picture if the underlying data or the underlying method were anything less than rigorous. It is something like standing in an open field long after a snowfall has melted away completely and still trying to work out from nothing but old measurements taken at the time whether two sets of footprints crossing that same field had ever actually met. That reconstruction finally became possible only very recently, and it fell to a young researcher at the very same university where the Radcliffe Wave itself had first come into focus. Ephraim Makoni, a doctoral researcher in astrophysics at the University of Vienna, led a team that set out to answer the question directly, working alongside several of the same scientists who had helped identify the wave in the first place, including Professor João Alves. In total, 17 researchers from institutions across multiple countries contributed to the effort, a reminder that a discovery like this rarely comes from a single scientist working alone in a quiet office, but instead from a wide, patient collaboration stretched across borders and time zones, each contributor checking and refining the other's work. Where Alves and his colleagues had spent their earlier work mapping the wave's shape and size, Makoni's project asked a narrower, more pointed question. Using everything now known about the wave's structure and motion, could anyone determine whether the sun had ever actually been inside it? And if so, precisely when? Answering that question required a very specific kind of evidence. Individual clouds of gas are notoriously difficult to trace backward through time with any real precision. Gas has no fixed shape, drifting and dispersing the way smoke does in open air, which makes its past position hard to pin down with any confidence. Stars, on the other hand, are a different matter entirely. Once a star forms, its position and motion can be measured with real precision using the very same Gaia data that had already helped reveal the wave itself, and that motion can be projected backward through the galaxy's gravity with real confidence, the same way a thrown ball's earlier position can be worked out if you already know its current speed and direction. Position alone was never going to be enough for a calculation like this. Knowing exactly where a star or a cluster sits today tells you nothing about where it used to be, unless you also know exactly how fast and in precisely which direction it has been moving all along. Gaia's true advantage lay in measuring both at once, position and velocity together, for every single star bright enough to detect, an achievement that would have been unimaginable to earlier generations of astronomers working with far cruder instruments. Even a small error in either measurement, multiplied across millions of years of backward projection, could easily throw a reconstructed path off by a wide enough margin to erase any genuine crossing entirely. Or worse, invent one that never actually happened. Getting the answer right meant getting every single input right first. Measuring the sun's own motion precisely enough for a calculation like this required combining several different kinds of observation. Radial velocity, how fast the sun appears to move directly toward or away from surrounding stars, can be measured by studying subtle shifts in starlight itself. The same basic principle used to measure the speeds of distant galaxies, just applied much closer to home, combined with Gaia's precise measurements of position and sideways motion across the sky that gave researchers a complete three-dimensional picture of exactly how the sun has been moving and exactly where that motion would have carried it at any point across the past 30 million years. Makoni's team turned to a very particular kind of star for this purpose. Open clusters, loose groupings of young stars born together out of the same collapsing cloud of gas, still huddled close together in the sky before the galaxy's gravity has had time to pull them apart. Other methods were considered and set aside. Simply tracking the wave's gas directly backward through time proved far too imprecise, since gas drifts, spreads, and mixes with its surroundings in ways that are difficult to model with any confidence over millions of years. Individual stars scattered at random throughout the region, meanwhile, carry too little connection to the wave's own history to serve as reliable markers of where the gas itself once stood. Open clusters offered the best of both worlds, precise enough to track individually the way Gaia tracks any ordinary star, while still carrying a close, physical connection to the very cloud of gas that gave rise to them in the first place. Anyone who has ever looked up and picked out the Pleiades with the naked eye has already seen an open cluster firsthand, a small, tight knot of stars, born together, still traveling together, though given enough time, tens or hundreds of millions of years. The gentle, constant tug of the rest of the galaxy will eventually pull even a cluster like that apart, scattering its stars across the sky until they no longer resemble a family at all, just distant individuals with a shared, forgotten birthplace. Because clusters like this form directly out of clouds like the Radcliffe Wave, and because they are still young, their current position and motion serve as an unusually faithful stand-in for the motion of the gas cloud that gave birth to them in the first place, even long after that original gas has drifted away or been consumed by new stars. The team selected 56 such clusters, every one of them associated with the Radcliffe Wave and every one of them still young, 30 million years old or younger, for their motion to closely track the wave's own drift through the galaxy. Using precise measurements of each cluster's current position, distance, and velocity, the researchers projected every one of those 56 paths backward through time, retracing each cluster's journey million by million years, working out where it must have been, and by extension, where the parental gas cloud it was born from must have been at any given moment in the ancient past. They performed the very same calculation for the Sun, projecting its own well-understood orbit backward across that same span of millions of years. Then came the actual test. At every point along that backward journey, how close did the Sun's reconstructed path come to each cluster's reconstructed path, and by extension, to the wave itself? To guard against wishful thinking, the team only accepted a crossing as meaningful when the odds of it being real, rather than a chance alignment, cleared a demanding statistical bar, and they repeated the entire calculation many times over, adjusting for the uncertainty built into every individual measurement to make sure the result held up under real scrutiny, rather than simply confirming what they had hoped to find. Before any of this became part of the accepted scientific record, the entire chain of reasoning also had to survive careful scrutiny from other astronomers entirely unconnected to the original research. Reviewers whose job is specifically to hunt for weaknesses, unjustified assumptions, or statistical shortcuts before a study is allowed to appear in a respected scientific journal. The research appeared in Astronomy and Astrophysics, one of the field's long-established peer-reviewed publications, only after clearing that process. The answer, when it finally came, was about as clear as this kind of reconstruction ever gets. The Sun's path and the wave's reconstructed path did not simply pass near each other at some point in the distant past. They actually overlapped, converging in the region of sky associated with the Orion star-forming complex, one of the very stellar nurseries already known to be threaded along the wave's great length. There is a certain poetry in exactly where that crossing took place. The Orion complex is not some obscure, forgettable patch of galaxy. It is one of the most photographed, most studied, most quietly beloved regions in the entire night sky, visible without any instrument at all on any clear winter evening, a stretch of sky people have been staring up at, wondering about for as long as anyone has kept written records. The very same stellar nursery responsible for some of the most striking astronomical photographs ever taken turns out to be the same stretch of galaxy the Sun itself was once quietly moving through, long before there was anyone alive to photograph anything at all. Generations of ordinary stargazers, checking the sky through a modest backyard telescope on a cold winter night, had unknowingly been looking directly at the very same patch of galaxy the solar system itself had once drifted through, without a single one of them ever suspecting the connection. Narrowing down exactly when that overlap occurred, the team calculated a crossing window stretching from roughly 18,200,000 years ago to roughly 11,500,000 years ago, with the closest approach, the moment the Sun would have been most deeply embedded in the wave's gas, falling somewhere between about 14,800,000 years ago and 12,400,000 years ago. In plainer terms, the Sun and the Earth, traveling quietly along beside it, appears to have spent something on the order of 6 to 7 million years, at various points across that stretch of ancient time, drifting through steadily denser and denser interstellar gas, brushing closest against the very heart of the Radcliffe Wave, somewhere close to 14 million years ago, during a stretch of galactic history long before anything resembling a human being or even a familiar, modern-looking mammal ever walked anywhere on Earth. To place that window in the story of life on the planet, this was an era when small, three-toed ancestors of the modern horse still roamed open grasslands, and when the first apes were only beginning to diversify into the branching family tree that would, tens of millions of years later, eventually include our own species, an outcome nothing alive at the time could possibly have anticipated. This was not a single dramatic night, some brief flash of cosmic drama visible from the ground. It was a slow, gradual immersion, stretched across a span of time, so long that entire mountain ranges could have risen and eroded away again before it finished. If any observer, human or otherwise, had somehow been standing on Earth's surface at the height of that crossing, the night sky itself would likely have looked subtly different, fainter, and hazier in certain directions, the way city lights blur and dim when viewed through a period of heavy fog or smoke, the extra dust and gas scattered along the line of sight quietly muting the light of more distant stars. No such observer existed to notice, of course. The Earth of 14 million years ago carried nothing capable of appreciating a night sky, let alone describing what it looked like. Whatever subtle dimming took place happened in complete silence, witnessed by nothing at all. The Radcliffe Wave crossing was not necessarily a once-in-the-solar system's lifetime event either. Across the full 225 to 250 million years it takes to complete one circuit of the galaxy, the solar system sweeps through an enormous range of different environments, some sparse enough to count as nearly perfect vacuum, others dense enough to qualify as genuine molecular clouds in their own right. Some of those earlier encounters, further back than current methods can reliably trace, may have gone completely unnoticed, their evidence long since eroded away, buried too deep, or simply never preserved in any rock or ice that has survived to the present day. The Radcliffe Wave crossing stands out not because it was necessarily unique, but because it happens to be recent enough, and modern tools happen to be precise enough for scientists to actually catch it, reconstructed in real detail, for what appears to be the first time anyone has managed to prove an encounter like this actually happened. What does it actually mean for a star system to pass through a structure like that? The Sun, like every star, does not simply sit exposed in open space. It is wrapped in an enormous bubble of its own making, called the heliosphere, formed by the constant outward rush of charged particles streaming off the sun's own surface, known as the solar wind. That bubble extends far beyond the orbit of every planet, pushing back against the thin gas of interstellar space and carving out a kind of sheltered clearing around the entire solar system. That boundary is not merely theoretical either. NASA's Voyager 1 spacecraft, launched in 1977 and still, remarkably, sending back data today, actually crossed the outer edge of the heliosphere in 2012, becoming the first human-made object to leave that bubble entirely and enter true interstellar space. Its sister craft, Voyager 2, followed in 2018. Both spacecraft are still out there right now, coasting silently through the very same kind of thin interstellar gas that fills most of the space between stars, each one carrying a golden record of Earth sounds and images along with it, in case it is ever found by anyone or anything capable of understanding what it holds. Even from their current vantage point, tens of billions of miles from home, both spacecraft still register the faint pressure of the surrounding interstellar gas pressing against their instruments, a real, measurable reminder that the boundary the solar system carries with it is not an abstraction, but a genuine physical edge, one that shifts and moves depending on exactly what kind of galactic neighborhood the sun happens to be drifting through at any given time. The heliosphere does more than simply mark a boundary. It also acts as a kind of shield, deflecting a good portion of the high-energy particles that constantly stream through the galaxy, known as cosmic rays, particles that would otherwise strike the inner solar system, including Earth, far more directly. A smaller, more compressed heliosphere offers a smaller shield, meaning more of that background radiation from deep space would have reached the inner solar system during the crossing than reaches it on an ordinary day. Untangling exactly what effect, if any, that extra radiation might have had is a separate and still unsettled question, one that scientists continue to study carefully rather than rushing to answer. Under ordinary circumstances, drifting through the kind of sparse, thin gas that fills most of the space between stars, the heliosphere holds its shape with relatively little trouble. The outward push of the solar wind winning the standoff against the surrounding gas by a fairly comfortable margin pushed that same bubble into a region as dense as the Radcliffe Wave, though, and the balance of that standoff shifts considerably. The denser surrounding gas presses inward from every direction, squeezing the heliosphere down to a noticeably smaller size, the way stepping off a sheltered porch and out into a stiff, driving wind might force a person to pull their coat in tighter around themselves. A smaller, more compressed heliosphere offers less overall shelter. Material from outside, gas and fine dust drifting through interstellar space, finds it easier to work its way in past the bubble's shrunken edge, penetrating deeper into the inner solar system, closer to the planets, closer to Earth itself than it would ordinarily be able to reach. None of this happened instantly either. The heliosphere did not simply snap to a smaller size and stay there. It would have compressed and relaxed gradually across the full multi-million-year span of the crossing, expanding and contracting somewhat as the solar system moved through pockets of slightly higher and slightly lower density within the wave itself, the boundary rarely perfectly still for very long. Earth itself carries a second, smaller shield of its own, a magnetic field generated deep within the planet's molten core, which deflects a further share of charged particles before they ever reach the ground, the same shield responsible for funneling particles toward the poles, and lighting up the sky there as the aurora. That second shield would have remained in place throughout the entire crossing, doing its part regardless of what was happening to the much larger heliosphere further out. But even Earth's own magnetic field cannot stop dust. Fine interstellar grains, electrically neutral and largely unaffected by magnetic fields, would have continued drifting down through the atmosphere and settling toward the surface, no matter how well protected the planet was from charged particles alone. That extra material matters because it does not simply stay out in open space. Some of it eventually settles into the inner solar system, drifting inward until a portion of it makes its way into Earth's own atmosphere, falling gently to the surface over time, mixed in with the ordinary dust already settling out of our skies on any given day. Calculations based on the density difference between the wave's gas and the far thinner space the solar system usually drifts through suggest that the amount of interstellar dust reaching Earth could have climbed dramatically during the crossing, potentially by a factor of anywhere from roughly 100 to as much as 100,000 times the ordinary background rate, depending on exactly how deep into the wave the solar system actually traveled at any given moment. Picture the difference between the thin, ordinary dusting that gathers on a windowsill over the course of an average week and the thick, choking blanket of dust that settled over entire towns during the worst storms of the 1930s. Dust Bowl and you have some sense of the range being discussed here, though spread across millions of years rather than a single afternoon. That extra interstellar dust carries something else along with it, something far harder to fake or misinterpret than a simple change in dust levels alone. Material drifting through interstellar space sometimes carries trace amounts of specific radioactive elements, forged long ago inside the violent deaths of massive stars. Elements such as iron-60, which barely exists at all under ordinary conditions here on Earth. Iron-60 decays away at a steady, well-understood rate, meaning any of it that formed naturally on Earth billions of years ago would have vanished long ago, decayed into other elements, and gone completely undetectable today. If a spike of fresh iron-60 were ever found in a layer of ancient ice or ocean sediment corresponding to a specific window of time, there is really only one honest explanation available. It arrived from somewhere outside the solar system, carried in on a wave of interstellar dust, deposited into Earth's geological record like a very particular kind of postmark, stamped onto an old letter, proving not just that the letter traveled, but roughly when and from which direction it came. This is not merely a theoretical possibility either. In a completely separate case, unrelated to the Radcliffe Wave itself, scientists have already found real spikes of iron-60 preserved in deep-sea sediments and even in samples of lunar soil, evidence of far more recent supernovae going off relatively close to the solar system sometime within roughly the last few million years. Those confirmed discoveries prove the basic detection method works. The open question, the one still waiting for a definitive answer here, is whether the far older, far fainter signature of the Radcliffe Wave crossing has left behind any similar trace of its own, buried deeper in the geological record and correspondingly harder to find. Finding evidence like that is painstaking work in its own right. Researchers drill long cylindrical cores down through layers of ancient ice in places like Antarctica, or down through undisturbed layers of mud on the ocean floor, each layer representing a distinct slice of time. Older the deeper the core goes, not unlike the rings inside a very old tree. By carefully dating each layer and testing it for the faint radioactive signature of elements like iron-60, researchers can, in principle, identify exactly which stretch of Earth's ancient past might carry the fingerprint of an encounter like the one the solar system is now believed to have had with the Radcliffe Wave, a fingerprint still waiting, in this particular case, for someone to go and look for it directly. That intense crossing did not last forever. By roughly 11,500,000 years ago, the solar system's continued motion around the galaxy carried it back out of the wave's densest gas and into thinner surroundings once again, the heliosphere gradually relaxing back outward as the external pressure eased. What happened next turns out to be a stranger and more separate story than it might first appear. The hollow, thin region of space the solar system drifts through today, known as the local bubble, did not appear by accident either, and it was not the Radcliffe Wave's doing at all. Astronomers now believe the local bubble began forming roughly 14 million years ago, when a chain of more than a dozen massive stars, born together and living fast, began dying one after another in a rolling series of supernovae, each explosion pushing the surrounding interstellar gas outward and widening a growing cavity, hollowing out a region roughly 1,000 light-years across. Its remaining gas heated to something close to 2 million degrees Fahrenheit, even as its density dropped to almost nothing at all. There is a real symmetry buried in that timeline. The very stellar explosions that hollowed out the local bubble also triggered fresh star formation along the bubble's own expanding edge, the shock waves compressing gas at the boundary just enough to trigger new collapses. New nurseries, new stars, flickering to life along the rim. Several well-known star-forming regions visible from Earth today sit directly on that boundary, a direct, physical consequence of the very supernovae that once hollowed out the space the solar system now quietly drifts through. At the time those explosions began, the Sun was not yet anywhere near that cavity, its own path through the galaxy still carrying it roughly 1,000 light-years away. It would take several more million years of travel before the Sun's continuing orbit finally carried it across the bubble's edge and into the hollow it now occupies near the center of. An arrival astronomers currently date to somewhere around 5 million years ago, a full 6 million years or so after the solar system had already emerged from its crossing of the Radcliffe Wave. Between those two events, drifting clear of the wave's dense gas and arriving inside the local bubble's hollow, the solar system appears to have spent several million years passing through some other, less thoroughly studied stretch of the galaxy. One more reminder that this entire journey has been continuous, without a single quiet, unchanging stretch anywhere along the way. Whatever mark the Radcliffe Wave crossing left behind, it was left millions of years before the solar system ever reached the calm, sparse hollow it currently calls home. Marconi and his colleagues have already suggested that their approach could be extended further, applied to other known structures scattered through the local galaxy, in the hope of building a more complete map of every dense region the solar system has drifted through across its long history, not just the one crossing this particular study set out to find. Future data releases from the Gaia mission, expected to sharpen the spacecraft's already remarkable precision even further, should allow researchers to narrow that window down even more tightly in the years ahead, refining the edges of the crossing with each new release of data. Finding that the timing lines up is only ever the first step in a much longer process, though. Anytime two events in the deep past appear to have happened around the same general stretch of time, a natural, very human instinct kicks in immediately, the urge to connect them, to assume one caused the other simply because they occurred close together. Careful scientists resist that urge, or at least try to. A shared timeline is a reason to look closer, to ask harder questions, to search for a specific physical mechanism linking one event to the other. It is never, on its own, proof of anything at all. So, the reconstruction holds. The sun did pass through the Radcliffe Wave, not as a rough guess or a tempting coincidence, but as the conclusion of a careful, repeatable calculation anchored to a specific place in the sky and a specific window of time, somewhere between about 18 million and 11 million years ago, with the deepest part of that crossing falling close to 14 million years ago. Every piece of that reconstruction, the 56 clusters, the backward traced orbits, the narrow window of overlapping time, points toward the same conclusion. The solar system was there, the Earth was there, riding along exactly as it always has, exactly as it still does today. What that ancient passage may have meant for the planet itself, whether it left any lasting mark at all, is a separate question entirely, one that reaches far beyond the motion of stars and gas clouds and into the deeper record kept in Earth's own rock and ice, waiting patiently for someone to go looking in exactly the right place, at exactly the right moment in time. 14 million years leaves very little behind in any form a person could hold in their hand. No photographs exist, no written records, no oral histories passed down across so vast a stretch of time. What survives, instead, is scattered, indirect, and stubbornly resistant to easy interpretation. Chemical traces locked inside ancient shells, the exact thickness and layering of ice sheets that have been building and reshaping themselves for millions of years since, the fossilized remains of plants and animals that lived and died long before anything resembling a human ancestor walked anywhere on the planet. Piecing together what actually happened to Earth's climate during this particular window means learning to read those scattered traces as carefully and as skeptically as a detective examining evidence at the scene of an event nobody alive was ever present to witness firsthand. That question, whether the Earth actually felt anything at all from the crossing, does not have a single tidy answer waiting in some drawer somewhere, ready to be pulled out and read aloud. What it has, instead, is a genuine mystery hiding in plain sight, one that begins not out in the depths of the galaxy at all, but right here, in the layers of ice and mud that Earth has been quietly laying down, one thin sheet at a time, for millions of years. Roughly 14 million years ago, around the very same stretch of deep time, the solar system is now believed to have been drifting through the heart of the Radcliffe Wave. Earth's climate underwent one of the most significant transformations of the last several 100 million years. Scientists call it the Middle Miocene climate transition, and long before anyone connected it to any structure out in the galaxy, paleoclimatologists had already documented it in careful, independent detail, using evidence that has nothing to do with astronomy at all. Paleoclimatologists rank it among the 3 most significant cooling episodes of the entire past 66 million years, a span of time called the Cenozoic era, encompassing everything that has happened on Earth since the extinction of the dinosaurs. The other 2 members of that short list are the Eocene to Oligocene transition, a much earlier and even larger cooling event roughly 34 million years ago that first established Antarctica's ice sheet in the first place, and the onset of Northern Hemisphere glaciation, a comparatively recent event only about 2,700,000 years ago that finally brought large ice sheets to the northern half of the planet as well. The Middle Miocene climate transition sits between those 2 events, a second great deepening of an icehouse world that had already begun, but had not yet finished, taking shape. Earth has not always been an icehouse world, a planet with substantial, permanent ice at its poles. For most of the planet's 4.5 billion-year history, average temperatures ran warm enough that little or no permanent ice existed anywhere, even at the poles. The current icehouse era, with substantial ice sheets at both ends of the planet, is, in the very long view of Earth's history, a comparatively unusual and relatively recent condition, one that began taking shape only across the last several tens of millions of years, with the Middle Miocene climate transition standing as one of the pivotal steps along that longer road. Before the transition began, Earth was coming out of a long, unusually warm stretch of its own history, a period some researchers call the Miocene climatic optimum, when global temperatures ran noticeably warmer than they do today, and Antarctica's ice cover remained far smaller and less stable than the vast, permanent sheet that covers the continent now. During that earlier warm period, global temperatures are estimated to have run several degrees warmer than today, warm enough that forests, rather than ice, may have covered significant portions of a continent now buried under mile after mile of solid ice. It was, in a sense, a preview of what a considerably warmer Earth actually looks like, preserved not in any human record, since no human existed yet to witness it, but in the fossilized pollen, leaves, and shells that quietly settled into the rock and sediment of the time. Then, across a relatively narrow window of time, the warmth gave way. Antarctica's ice sheet expanded dramatically, swelling towards something close to the volume it holds today, locking away such an enormous quantity of the world's water that global sea levels are estimated to have fallen by something on the order of 140 feet, an amount almost impossible to picture, roughly equal to the height of a modern office tower, 14 stories tall, all of it drawn directly out of the ocean and frozen solid at the bottom of the world. Before the transition, Antarctica likely still carried substantial ice across parts of its interior, but with far less coverage, far less permanence, and considerably more exposed, ice-free ground around its edges than the continent shows today. By the time the transition had run its course, Antarctica had become recognizably similar to the frozen continent explorers, and scientists would eventually encounter, thousands of years later, a landscape buried under ice more than a mile thick in many places, holding within it the overwhelming majority of the fresh water currently locked away anywhere on the planet. Ice sheets, once they begin forming in earnest, tend to reinforce their own growth. Fresh snow and ice reflect far more sunlight back into space than open ground or open ocean water ever could, meaning a growing ice sheet cools its own immediate surroundings simply by existing, encouraging still more snow to accumulate and survive through the following summer rather than melting away. That feedback loop, once it gains real momentum, can carry an ice sheet toward a much larger, more stable size than the initial cooling alone might have predicted, a slow, self-reinforcing process, playing out over hundreds of thousands of years, rather than any single dramatic season. Ocean temperatures fell as well, though not evenly. In the deep water, far below the surface, the cooling was comparatively modest, somewhere in the range of 4 to 5 degrees Fahrenheit. Nearer the surface, especially in the Southern Ocean surrounding Antarctica, the cooling appears to have been considerably sharper in some records, as much as 11 to 13 degrees Fahrenheit. enough to meaningfully reshape which plants and animals could survive across huge stretches of the planet. A shift of only a few degrees might sound modest, easy to dismiss as unremarkable, especially set against the scale of everything else being discussed in this story. But climate systems tend to respond to small, sustained changes far more dramatically than intuition suggests. A few degrees of average cooling, held steady across hundreds of thousands of years, rather than fluctuating back and forth as ordinary weather does, is enough to shift the entire boundary between where ice permanently survives the summer and where it does not, enough to turn a seasonal snowpack into a permanent ice sheet that keeps growing year after year rather than melting back to nothing each spring. None of this comes from guesswork. Scientists reconstruct ocean temperatures and ice volume from millions of years ago using a method that relies on oxygen itself. Oxygen atoms come in a few slightly different varieties, called isotopes, weighing very slightly different amounts from one another, and the exact ratio between those varieties, locked permanently into the tiny shells of ancient sea creatures as they lived, fed, and eventually died, works something like a thermometer. Nobody realized they were leaving behind. As those shells settled to the ocean floor and became buried under millions of years of subsequent sediment, they preserved that ratio faithfully, layer after layer, each one quietly recording the temperature and the ice conditions of the ocean at the moment it formed. Oxygen is not the only element that leaves a readable trace. Carbon, too, comes in slightly different isotope varieties, and its own ratio, also preserved in ancient shells and sediment, offers scientists a rough window into how the planet's entire carbon cycle, the constant exchange of carbon dioxide between air, ocean, rock, and living things, was behaving at any given moment in the deep past. Reading oxygen and carbon isotopes together, cross-checking one against the other, gives researchers a far more complete and reliable picture than either measurement could provide entirely on its own. The same way, comparing two independent witnesses tends to produce a more trustworthy account than relying on just one. By drilling down through those layers today and carefully measuring the isotope ratios locked inside, researchers can reconstruct a remarkably detailed timeline of Earth's ancient climate, entirely independent of anything happening out among the stars. Much of the evidence supporting this timeline comes from an ongoing, decades-long international effort called the Ocean Drilling Program and its modern successor, which has sent specially designed research vessels out across every major ocean on Earth, lowering drilling equipment thousands of feet down through open water, and then hundreds of feet further into the seafloor itself, retrieving cores of ancient mud and rock that would otherwise remain forever out of reach. Ships built for exactly this purpose spend months at a time far from any coastline, their crews carefully cataloging and preserving every single core the moment it reaches the deck, aware that a few feet of ordinary-looking mud might hold a more reliable record of Earth's ancient climate than any written account ever could. Much of the physical evidence for Antarctica's own ice history comes from cores drilled directly through the ice sheet itself, in some of the most remote, difficult research locations anywhere on the planet, where scientists and support crews spend months at a time working in conditions that regularly reach temperatures cold enough to freeze exposed skin within minutes. The ice retrieved from those cores does not just record temperature. Tiny bubbles of ancient air, trapped and sealed the moment each layer of snow compressed into solid ice, preserve actual samples of the atmosphere itself from millions of years in the past, giving researchers something remarkably close to a direct measurement of ancient carbon dioxide levels, rather than an indirect estimate reconstructed from some other proxy entirely. The transition reshaped more than ice and ocean temperature alone. Fossil records from the period show a broad reorganization of marine life as well, with many species adapted to the earlier, warmer conditions declining or disappearing from large stretches of the ocean, gradually replaced by species better suited to the cooler, more variable world that followed. On land, the cooling and the drying that came with it favored the spread of open grasslands at the expense of denser, more water-hungry forests across large stretches of the globe, part of a broader shift already underway across the Miocene as a whole. Grazing animals with teeth built for tougher, more abrasive grasses, rather than soft leaves, began to spread and diversify in response. One small example of how a shift measured in a handful of degrees, sustained long enough, can quietly reshape which forms of life thrive and which ones struggle across an entire planet. Some of those changes are still visible today in the fossil record found across multiple continents, laid down in rock formations that geologists continue to study for exactly this kind of evidence. So what actually caused a transformation of that scale? The leading explanation, built up over decades of careful research, entirely separate from any question about the Radcliffe Wave, centers on a substantial decline in atmospheric carbon dioxide, estimated at somewhere around 100 parts per million, occurring in the several 100,000 years leading directly into the transition. Exactly what drove that decline remains an active area of research in its own right, with leading candidates including a slowdown in volcanic activity that had previously been pumping carbon dioxide into the atmosphere, and an increase in the weathering of exposed rock, a slow chemical process accelerated by the ongoing uplift of the Himalayan mountains on the far side of the planet, that gradually pulls carbon dioxide out of the air and locks it into rock and sediment instead. That weathering process works slowly but relentlessly. Rainwater, slightly acidic simply from absorbing carbon dioxide out of the air as it falls, reacts with exposed rock over time, gradually breaking it down and carrying the resulting minerals toward the sea, where they are eventually locked away in new layers of sediment. Carbon dioxide and all raise a mountain range high enough, expose enough fresh rock to that same slow rainwater over long enough a stretch of time, and the cumulative effect on the planet's entire atmospheric carbon budget can become substantial, even though the process itself, at any given moment, looks like nothing more dramatic than rain falling on stone. As atmospheric carbon dioxide fell, the greenhouse warming it had been providing fell along with it, and the door opened for Antarctica's ice to expand in a way it simply could not while the planet remained warmer. That falling carbon dioxide level did not act alone. Researchers studying the transition have also pointed to a subtle astronomical rhythm, a period of unusually low eccentricity in Earth's own orbit around the Sun, meaning Earth's path was, for a stretch of time, closer to a perfect circle than usual. This kind of orbital influence on climate is not unique to the Middle Miocene. Earth's orbit around the Sun is never perfectly fixed. It stretches slightly into a more oval shape and then relaxes back toward a circle again, cycling gradually over roughly 100,000 years, part of a broader family of slow orbital rhythms that astronomers have linked to the timing of ice ages throughout Earth's more recent history as well. During the run-up to the Middle Miocene climate transition, that cycle happened to fall into one of its flatter, more circular phases, one small piece of celestial choreography working alongside the falling carbon dioxide rather than against it, producing steadier, less variable seasons that helped newly forming ice sheets survive their first vulnerable summers, rather than melting back away each year, effectively priming the climate system for the ice sheet growth that followed. Separately, deep beneath the Southern Ocean, the gradual sinking of ancient seafloor near what is now the Scotia Sea, close to the southern tip of South America, may have allowed a powerful ring of ocean current to finally establish itself in full around Antarctica, thermally isolating the continent from warmer waters further north. The way pulling a heavy curtain closed can isolate a room from the rest of a drafty house. Checking that overlap was itself a deliberate, careful step, not an accidental discovery stumbled upon after the fact. Once Marconi's team had established the crossing window with real confidence, they specifically went looking through the existing paleoclimate literature for any major, independently documented shift in Earth's own history that happened to fall within that same span of time. The Middle Miocene climate transition, already well known to paleoclimatologists working in a completely separate corner of science, was waiting there to be found. Here is where the story bends back toward the stars. When researchers lined up the best available dating for the Middle Miocene climate transition against the crossing window calculated for the Radcliffe Wave, the two timelines did not simply occur in the same general era of Earth's history. They overlapped closely. The transition is generally dated to somewhere between about 14,800,000 years ago and 12,900,000 years ago. The solar system's closest approach to the heart of the wave, as calculated by Marconi's team, fell somewhere between about 14,800,000 years ago and 12,400,000 years ago. Line those two windows up side by side, and they are, for all practical purposes, describing the same stretch of deep time. That kind of overlap does not happen only in the imagination of people looking for a connection. It is the sort of coincidence that earns a second look from careful scientists, and the physical link researchers have proposed runs directly through material already introduced earlier in this story, interstellar dust. During the deepest part of the crossing, with the heliosphere compressed and the flow of outside material into the inner solar system running far above its normal rate, a meaningfully larger quantity of fine dust would have been raining gently into Earth's upper atmosphere across those millions of years. The individual grains involved in all of this are almost inconceivably small, some no larger than the fine particles that make up ordinary smoke or haze, others smaller still, closer in scale to individual strands of spider silk. Billions of grains that size, scattered high across the upper atmosphere rather than concentrated in any one place, are enough to noticeably dim sunlight over an entire hemisphere without a single one of them ever being visible to the naked eye from the ground. Dust, suspended high in the atmosphere, does not simply sit there invisibly. It scatters and reflects a portion of incoming sunlight back out into space before that light ever reaches the surface. The same basic principle behind the dimmed, reddened sun that sometimes hangs in the sky during a bad wildfire season, when smoke particles fill the upper air and visibly cut the sunlight reaching the ground below. Anyone who has stepped outside during one of those smoke-heavy afternoons and noticed how the temperature seems to drop slightly as the haze thickens overhead, has experienced a small, fast version of the same basic physics potentially at work here, stretched out, instead, across a span of millions of years rather than a single day, and operating on dust drifting in from interstellar space rather than smoke drifting in from a nearby forest fire. Enough of that kind of scattering, sustained not for a single smoky afternoon, but across a period of millions of years, could, in principle, measurably cool a planet's surface, the same broad mechanism on a vastly different timescale that causes a single large volcanic eruption to cool global temperatures for a year or two after its ash reaches the upper atmosphere. This is exactly the point in the story where honesty matters most. Marconi and his colleagues did the arithmetic themselves, calculating just how much additional cooling the extra interstellar dust could plausibly have produced during the crossing, and their own conclusion was appropriately cautious. By their own estimate, the resulting cooling effect likely falls well short, potentially by a very wide margin, of what would be needed to explain the full scale of the Middle Miocene cooling on its own. In the researchers' own assessment, the well-established decline in atmospheric carbon dioxide remains the most likely primary explanation for the transition, though, by their own admission, considerable uncertainty still surrounds the full picture. The honest conclusion is not that the Radcliffe Wave caused an ice age. It is that a real, independently confirmed shift in Earth's climate happened to occur during the very same narrow window of time that the solar system was passing through a genuinely denser stretch of the galaxy, and that the physical mechanism connecting the two, extra interstellar dust settling into the atmosphere, is real and measurable, even if its total contribution appears to have been a secondary one at most, a single log added to a fire that was already blazing from a dozen other logs entirely. None of this makes the interstellar dust mechanism meaningless or unworthy of attention. Real contributing factors matter, even modest ones, and demonstrating that a measurable physical pathway genuinely exists, connecting a specific galactic event to a specific planetary one, is a legitimate and valuable scientific achievement in its own right, regardless of how large or small its ultimate share of the credit turns out to be. It is worth asking why researchers would bother publishing a finding at all if their own calculations suggest it was, at most, a secondary contributor to something as significant as an ice age. The answer says something important about how science actually works, day to day, out of the public eye. Very few discoveries arrive as a single, tidy, world-changing revelation. Far more often, understanding builds gradually, one carefully documented piece at a time, each new piece narrowing the range of what remains possible, ruling some explanations out, and lending modest support to others, until, eventually, often after years or decades of contributions from many different research groups, a fuller picture begins to emerge. A confirmed physical mechanism, even a modest one, is a genuine piece of that larger puzzle, worth documenting carefully and precisely, regardless of whether it turns out to be the star of the story or a quiet supporting player standing just off to one side. Confirming the connection directly would require finding something quite specific, a measurable spike in extraterrestrial material, whether interstellar dust itself or the trace radioactive signatures it can carry, preserved in rock or ice layers that can be reliably dated to the same narrow window as the Middle Miocene climate transition. Unlike the more recent examples already found in younger ice and seafloor samples, evidence from a crossing this old faces a much steeper challenge. 14 million years is an immense stretch of time for any thin, delicate signal to survive undisturbed, buried under everything that has settled, shifted, and compressed on top of it since. Finding a layer of ocean sediment or ancient rock old enough, undisturbed enough, and precisely dated enough to test this particular question directly remains, for now, a real and unsolved challenge in its own right, one that may take years of careful fieldwork to overcome, if it can be overcome at all. Somewhere in a freezer, at a research facility, or still buried under the Antarctic ice sheet itself, the specific layer of evidence that could settle this question outright may already exist, entirely unexamined, waiting for exactly the right combination of curiosity, funding, and careful laboratory work to bring it to light. There is an old, useful piece of caution scientists apply to situations exactly like this one, and it is worth sitting with for a moment. Picture 2 church bells in 2 separate towns miles apart, each one on its own separate clockwork, each one wound and maintained by a different keeper who has never met the other. Every so often, purely by the accident of their separate mechanisms, both bells happen to strike the hour at exactly the same moment. Anyone standing exactly between the 2 towns on such a day might reasonably wonder whether one bell's ringing somehow triggered the other, but the honest answer in that case would be no. The 2 clocks simply share a great deal of structure in common, both built to strike at the top of the hour, and once in a while that shared structure lines their timing up perfectly without either one causing the other to ring at all. A shared timeline invites a closer look. It does not, by itself, prove a shared cause. Extraordinary claims, the kind that would rewrite a settled corner of Earth's climate history, require correspondingly strong evidence before they can be accepted, and for now, the direct physical evidence linking this specific crossing to this specific cooling, a measurable spike of interstellar material actually found in the rock or ice from exactly the right window of time, simply does not exist yet. It may exist and simply not have been found. It may never be found at all. Both possibilities remain genuinely open. Findings like this one increasingly sit at the boundary between fields that used to operate almost entirely separately from one another. Astronomers spent decades mapping the structure and motion of gas and stars without giving much thought to Earth's own geological record, and paleoclimatologists spent decades reconstructing ancient temperatures and ice volumes without giving much thought to what the solar system might have been doing among the stars at the same moment. Work, like Marconi's, sits directly at that intersection, requiring genuine fluency in both galactic structure and Earth's own deep climate history. That kind of cross-disciplinary collaboration is becoming steadily more common across modern science generally, as the tools available in one field, precise stellar positions from a spacecraft like Gaia, for instance, turn out to have genuine, unexpected relevance to questions being asked in an entirely different field many people would never think to connect it to. This is not likely to be the only ancient climate puzzle astronomers go looking through for a matching galactic explanation either. Earth's deep climate history contains numerous other transitions, warmings, coolings, and abrupt shifts that remain only partially explained by conventional causes alone. Now that one research team has demonstrated a workable method for checking whether any particular climate shift lines up with a documented passage through a dense region of the galaxy, other scientists studying other ancient transitions may well begin asking the very same question about events in their own corner of Earth's history, treating the solar system's galactic address, so to speak, as one more piece of context worth checking alongside the more traditional factors. Every piece gathered so far, the timing, the physical mechanism, the researcher's own careful arithmetic, points toward the same measured, appropriately uncertain conclusion, neither dismissing the connection outright, nor overselling it into something the evidence does not yet support. Whether the Radcliffe Wave crossing genuinely nudged Earth's climate during the Middle Miocene climate transition, contributing some small additional push alongside the falling carbon dioxide and the shifting ocean currents, or whether the timing is simply one of history's more striking coincidences, remains an open question, one that will likely require searching Earth's own ice and rock directly for a very particular kind of evidence before it can be settled with any real confidence. What is no longer in question is the larger fact sitting underneath all of it. The solar system does not travel through the galaxy in isolation from the planet riding along inside it. Whatever the sun passes through, Earth passes through as well, and this ancient crossing, real, dated, and reconstructed in careful detail, is only one entry in a much longer, still unfolding account of everywhere this small, quiet corner of the galaxy has been, and everywhere it is still going. 14 million years is a difficult number to hold onto for very long, difficult enough that it can start to feel almost abstract, more like a mathematical curiosity than a real, lived stretch of time that actually happened. One ordinary moment after another, the same way any other stretch of time has ever actually happened. It helps, sometimes, to come back to the present moment before going any further, to remember exactly where all of this ancient history has actually led. Right now, tonight, as this story reaches you, the solar system sits inside that same quiet hollow, already described earlier in this video. The local bubble, a stretch of unusually thin, unusually hot space carved out by supernovae long before the sun ever arrived there. What has not yet been said is just how centrally the sun sits within it. Current measurements place the sun almost precisely at the middle of that 1,000 light-year hollow, a position some of the very researchers who mapped it have openly described as little more than a fortunate accident of timing, the sun simply happening to drift into the bubble's interior at more or less the same stage in its slow growth that placed the center closest to where the sun's own orbit happened to carry it. There was no plan behind that alignment, no deeper design, only the ordinary physics of one slow-moving star intersecting one slowly expanding cavity, at more or less the right moment for the two to end up sharing the same address. That positioning shapes the sky overhead in ways easy to take for granted. Because the solar system sits inside such an unusually empty stretch of space, the interstellar gas and dust that would otherwise dim and redden starlight passing through it barely gets in the way at all here. At least for now, stars visible from Earth on any given clear night appear close to their true, undimmed brightness, unfiltered by the kind of dense, obscuring material that fills so much of the wider galaxy beyond this particular hollow. In a strange sense, part of what makes tonight's sky look the way it does, clear, bright, dotted with countless visible points of light, is owed directly to a chain of ancient stellar explosions that happened to hollow out this exact patch of galaxy millions of years before anyone existed to appreciate the view. That clarity will not last forever, at least not on any human timescale, though certainly on a scale far beyond anything a single human life could measure. The local bubble is not a fixed, static room the solar system happens to be sitting in. It continues expanding even now, slowly pushing its own boundary outward, its edges still glowing faintly with the star formation the original supernovae originally triggered. Eventually, whether in a few million years or considerably longer, the solar system's continuing orbit will carry it across that ever-shifting boundary once again, out of this particular hollow and into whatever kind of galactic neighborhood happens to lie beyond it. Sparse or dense, calm or turbulent, impossible to know in any detail from here. The local bubble does not sit in isolation, either. Maps of the surrounding interstellar gas reveal that its walls, the denser shell of gas marking its outer boundary, are broken through in several places by narrow, low-density passages, something like tunnels connecting the local bubble to other similar hollow cavities scattered nearby, including one associated with the Pleiades star cluster already mentioned earlier in this account. Rather than a single, isolated room, the solar system's neighborhood looks, at this larger scale, more like one chamber in a loosely connected honeycomb of similar cavities, each one carved out by its own local population of supernovae, each one linked to its neighbors by these thin, sparse corridors of even emptier space. 7 well-known stellar nurseries sit directly along the surface of this bubble, precisely where the outward-pushing shell of gas has been compressed just enough, at exactly the right density, to collapse into new stars. The Orion complex, already introduced earlier in this account, as the very region the Radcliffe Wave crossing took place within, is one of them. Taurus is another. A visible band called the North America Nebula, named for its rough resemblance to the shape of that continent when viewed through a telescope, sits along that same bubble surface, another quiet nursery where fresh stars continue condensing out of leftover gas even now. One more example of destruction, in the form of ancient supernovae, quietly seeding new creation along the very boundary it carved. Together, these surface regions account for essentially every young star currently forming anywhere near the Sun, meaning that nearly every new star visible through a backyard telescope from Earth tonight, if it is young enough to still be surrounded by the glowing nursery it was born from, very likely owes its existence to the same ancient supernovae responsible for hollowing out the local bubble in the first place. Zoom out even further, past the local bubble, past the Radcliffe Wave, past the entire local arm of spiral structure containing both of them, and this whole story shrinks down to a genuinely tiny corner of a genuinely enormous galaxy. The Milky Way holds a few 100 billion stars, spread across a disk roughly 100,000 light-years wide, and everything described across this entire account, the wave, the crossing, the local bubble, the Sun's own careful 20-lap history, has all taken place within a volume of space that would barely register as a single point on any map drawn at the true scale of the galaxy as a whole. Human beings have occupied this particular corner of that vast structure for what amounts to a single, barely measurable instant of the galaxy's own much longer history, and yet, in that brief instant, have managed to build instruments precise enough to trace the ancient path of an entire star system through structures that took millions of years to even drift past. That capability did not exist even within living memory. It exists now, tonight, quietly doing its work somewhere far overhead, long after most of the people responsible for pointing it skyward have gone to sleep themselves. Earlier in this account, the solar system's long circuit around the galaxy was compared to a carousel that turns only once every 225 to 250 million years, with the Sun having completed something like 20 full turns of it since its own formation. That comparison carries a natural continuation worth sitting with now. 20 turns down does not mean the ride is anywhere close to finished. The Sun still holds enough nuclear fuel to keep shining for roughly 5 billion more years, long enough for perhaps another 20 turns around the galaxy to unfold after this one. Each lap carrying the solar system through yet another unpredictable sequence of galactic neighborhoods, dense clouds, and empty gulfs, alternating in a pattern nobody alive today could ever hope to fully chart in advance. Nobody today can say with any real confidence exactly what those future laps will carry the solar system through. Perhaps another wave, much like this one. Perhaps a stretch of space even emptier than the local bubble currently is. Perhaps, eventually, another slow drift through the crowded, star-forming heart of a spiral arm not unlike the one containing Orion. Whatever lies ahead, the solar system will meet it the same way it appears to have met the Radcliffe Wave, gradually, almost imperceptibly, the heliosphere compressing and relaxing as it always has, Earth's climate quietly registering whatever small additional influence drifts in with the changing scenery, largely without anyone alive at the time even noticing the shift was underway. Not every structure the solar system's long journey might someday encounter is made of gas either. Earlier in this account, brief mention was made of an entirely different kind of galactic structure, the tattered stellar streams left behind when smaller star clusters and dwarf galaxies get slowly torn apart by the Milky Way's gravity, an entire family of long, thin rivers made of individual stars rather than clouds of drifting gas and dust. Some of these streams already carry names of their own, discovered and mapped using the same kind of precise stellar surveys that revealed the Radcliffe Wave. The Sagittarius stream wraps almost entirely around the Milky Way, a long ribbon of stars stripped from a small galaxy that wandered too close and paid for it with its own slow disintegration. Closer to home, a thinner stream, sometimes called GD1, threads through the galaxy's outer reaches, so narrow and so faint that it went completely undetected until modern surveys finally had the precision to trace it. Where the Radcliffe Wave is a river of gas, curling and rippling through the disk of the galaxy, these streams are rivers of stars, tracing similarly graceful arcs across the sky, born from an entirely different kind of cosmic violence. The solar system has already drifted near several such streams over the course of its long history, and will likely drift near others in the ages still ahead. One more reminder that a night sky full of what looks like scattered, disconnected points of light is, in truth, threaded through with far more structure and history than it first appears to hold. Step back far enough, and the shape of this entire story comes into focus. 6 years ago, astronomers did not know the Radcliffe Wave existed at all. A little over a year after that, they had not yet worked out whether the solar system had ever actually touched it. Only very recently has anyone been able to say, with real confidence, not just that the crossing happened, but roughly when and roughly where, and to propose, cautiously, a specific physical thread connecting that crossing to a documented shift in Earth's own ancient climate. Every piece of that timeline belongs to living memory. Somewhere out there tonight, likely on this very continent, sit scientists who remember clearly what it felt like before any of this was known at all. Back when the space around the sun was assumed to be reasonably well understood, mapped, settled, unremarkable. It was not. It never really is. Every generation of astronomers before this one also assumed their map of the local sky was more or less complete, and every generation eventually found out otherwise. The astronomers who first proposed the Old Gould Belt back in the 1870s believed just as confidently in their own picture of the local sky as anyone believes in the Radcliffe Wave today. So did the generations who followed them, refining that same ring-shaped model decade after decade, publishing paper after paper built on an assumption that later turned out to be wrong. None of that earlier work was foolish or careless. It was simply built with the tools available at the time, tools that, however impressive for their era, were never going to be capable of revealing a structure as subtle as a single, long, gently rippling wave of gas. Anyone who sat through an astronomy class in the middle of the last century learned a night sky described with a confidence that, in hindsight, looks almost quaint. Textbooks from that era described the sun's neighborhood in simple, settled terms: a scattering of nearby stars, a handful of catalogued nebulae, and little sense that any of it might connect into some larger, hidden architecture. The star charts and planetarium shows many people first encountered as children, often projected onto a domed ceiling in a school gymnasium or a local museum, presented the night sky as something essentially finished, a fixed catalogue of named stars and constellations, rather than a living, evolving structure still actively being mapped. That was never anyone's fault. It was simply the honest snapshot available at the time, built from telescopes and calculations that, for all their genuine sophistication, could not yet see the kind of three-dimensional structure Gaia would eventually reveal. The same students who once memorized that older, simpler picture are, in many cases, still alive today, watching that same picture get quietly redrawn in real time by instruments and methods nobody in their original classroom could have imagined. Every generation gets its own defining astronomical moment, the achievement that becomes, in hindsight, the marker separating one era of understanding from the next. For an earlier generation, that moment arrived with grainy television footage of boots touching lunar dust for the first time. For this generation, it may well turn out to be something quieter, less visually dramatic, but arguably just as significant: the slow, patient construction of an accurate three-dimensional map of the galaxy's own local structure, built not from a single dramatic voyage, but from a spacecraft spinning quietly in place, measuring the same patch of sky over and over again for years, until an entire hidden architecture finally came into focus. That quieter kind of achievement rarely gets its own ticker-tape parade. It deserves one anyway. Astronomers sometimes describe the current period as something of a golden age for mapping the galaxy's own architecture. A stretch of years when a single spacecraft mission finally provided the precision needed to move beyond guesswork and actually measure, rather than merely estimate, the true three-dimensional shape of the space surrounding the sun. Every discovery described across this account, the wave itself, its motion, the crossing, even the ongoing work extending outward from all of it, traces back to that same single mission, still operating, still gathering data, still quietly rewriting the map of the only galactic neighborhood human beings have ever called home. None of it happened in isolation either. Alves, Goodman, and Zucker, who first traced the wave's shape, Konietzka, who proved it was truly moving, Marconi, and his 16 co-authors, who worked out when and where the sun had passed through it. Behind every one of those names sit dozens more researchers, technicians, and engineers who built and maintained the Gaia spacecraft itself, kept it pointed correctly, calibrated its instruments, and processed its billions of individual measurements into something usable. A discovery like this is never really the work of one person alone, however tidy that might sound in the retelling. It is the slow, patient accumulation of thousands of careful hours, spread across dozens of people, most of whose names will never appear in any documentary at all. The scientists at the center of this particular story have not stopped working either. Alves continues studying the structure and history of the galaxy's local neighborhood from his position at the University of Vienna, the same institution where Marconi carried out the detailed reconstruction connecting the sun's path to the wave zone. Their research groups continue refining both halves of this story even now, tightening the crossing window as new data arrives, and watching for any fresh evidence, geological or astronomical, that might eventually settle the open question of just how much of an imprint that ancient crossing actually left behind. Whoever eventually goes looking for that missing piece of evidence, whether in an ice core drilled next year or a sediment sample studied a generation from now, will be continuing a project that began, in its own quiet way, with a fellowship year in Massachusetts and a spacecraft launched more than a decade ago. One small, patient link in a chain of curiosity that shows no sign of running out. And that same humility applies to the question this particular story leaves open: whether the Radcliffe Wave genuinely reached down and touched Earth's climate in some small, real, physically traceable way, or whether the timing was simply one of the more striking coincidences the deep past has to offer, is not yet settled, and it may not be settled for a long while yet, if it ever is settled at all. That is not a disappointing place to end. It is, if anything, the most honest place available. Consider everything already gathered across this account. A slow decline in atmospheric carbon dioxide, driven by mountains rising and rocks slowly dissolving in ordinary rainwater on the far side of the planet. A subtle flattening in the shape of Earth's own orbit around the sun, priming new ice for survival through its first fragile summers. The gradual deepening of an ocean gateway near the tip of South America, finally allowing a ring of current to seal Antarctica off from warmer water. And now, cautiously, tentatively, a possible fourth voice added to that chorus. A wave of interstellar gas the solar system happened to be drifting through at exactly the same stretch of ancient time. No single one of those four threads acts alone. Earth's climate has never had a single author. It has always been a collaboration, negotiated among forces, operating on scales from a single raindrop, striking a single stone to an entire star system, drifting through the structure of its home galaxy. Whatever else remains unresolved, one plain, verifiable fact anchors the whole of tonight's account. The numbers hold up. Independent teams, working with independent instruments, using independent methods, arrive separately at the discovery of the wave, the confirmation of its motion, and the reconstruction of the sun's ancient path through it. Paleoclimatologists, working in an entirely separate branch of science with no interest whatsoever in galactic structure, independently documented Earth's own ancient cooling using evidence that has nothing to do with astronomy at all. Only afterward did anyone notice how closely those two independent timelines happened to align. That kind of convergence, several different lines of careful, unrelated evidence quietly pointing toward the same narrow window of time, is precisely the kind of pattern that earns real scientific attention, whatever the eventual answer to the deeper question turns out to be. Every one of the numbers cited across this account, the length of the wave, the timing of the crossing, the scale of the cooling, the magnitude of the carbon dioxide decline, traces back to a real, published, peer-reviewed source, checked and rechecked, before ever making its way into tonight's account, precisely because a story built on real evidence deserves nothing less than real, careful sourcing. Making that answer more precise remains the real work still ahead. Future ice cores drilled deeper and dated more precisely. Future ocean sediment samples checked specifically for the narrow signature this particular crossing would have left behind. Future data releases from Gaia and the missions that will eventually follow it, sharpening the crossing window still further. Evidence will not necessarily have to come from Earth alone either. The Moon, lacking any atmosphere, any weather, or any of the geological churn that constantly reshapes Earth's own surface, tends to preserve very old surface material with far less disturbance than anything found here. Material collected from the lunar surface, brought back by earlier crewed and robotic missions and still being studied today, offers scientists another possible archive to search, one considerably less disturbed by the intervening millions of years than anything buried under Earth's own restless geology. Somewhere in Antarctica, tonight, in the middle of a summer research season that looks nothing like summer anywhere else on the planet, researchers are very likely still out on the ice, drilling, measuring, and cataloging, extending the very same record this account has drawn from, one careful core at a time. Somewhere, in a laboratory, technicians are running isotope measurements on samples collected years earlier, patiently working through a backlog that never seems to shrink. None of that work happens quickly, and very little of it happens with any fanfare. It simply continues, season after season, decade after decade, building the foundation that discoveries like the one described tonight eventually get to stand on. Each of these future steps, small and unglamorous as any one of them might sound described individually, represents another careful attempt to turn an intriguing coincidence into either a confirmed connection or a settled non-connection, either outcome equally valuable, equally worth the careful years of work it will likely take to reach it. The two Voyager spacecraft, already introduced earlier in this account, will not keep transmitting forever, for what it is worth. Both are expected to run out of the electrical power needed to operate their instruments and communicate with Earth sometime within the next several years, after which they will continue drifting silently outward regardless, carrying their golden records into the depths of the galaxy long after any human hand last adjusted their course. In a sense, they are already beginning their own version of the same journey the entire solar system has been making all along, passing beyond the reach of easy observation, out into whatever unknown galactic neighborhoods happen to lie ahead of them, this time without even a radio signal left to report back what they find. The same basic principle likely applies well beyond Earth to any planet orbiting any star anywhere in the galaxy rides along on that star's own journey through changing interstellar environments, passing through its own sequence of dense clouds and empty gulfs across its own multi-billion-year history. The James Webb Space Telescope and instruments like it continues searching the atmospheres of distant worlds for hints of their own climate histories, even now, though untangling anything as subtle as a single ancient galactic crossing from that much farther away remains, for the foreseeable future, well beyond what any instrument can currently manage. Wherever life might exist on some distant world circling some distant star, its own planet's climate has likely been shaped in ways local scientists there may or may not ever discover by encounters with structures not unlike the Radcliffe Wave. Structures that same distant civilization would need its own version of a Gaia spacecraft and its own version of careful, patient researchers like Alves and Marconi to ever properly uncover. None of that needs to be frightening, and none of it needs to be resolved tonight to be worth sitting with for a moment before sleep. The wave that may or may not have nudged an ancient ice age into being finished its crossing millions of years before anything alive today existed to notice it, and whatever role it played, large or small or none at all, that role has already been played out, quietly, completely, without any further consequence still hanging over the present moment. There is a particular kind of comfort available in stories like this one, precisely because they resist neat, tidy endings. A mystery fully solved closes a door. A mystery honestly described, its edges acknowledged rather than smoothed over, leaves something gentler behind, an invitation to keep wondering rather than a demand to keep worrying. Nothing about tonight's story requires anyone listening to solve anything, verify anything, or carry any particular conclusion forward into tomorrow. The wave crossed, the ice grew, the carbon dioxide fell. The question of exactly how those three threads relate to one another can simply sit there, unresolved, patient, the way it has already sat, unresolved and patient, for 14 million years, waiting without any particular urgency, for whoever eventually gets around to answering it. There is something to be said, too, for the particular scale of comfort. A story spanning 14 million years can offer a single, ordinary evening. Whatever concerns tonight might otherwise be carrying, whatever kept sleep at a distance before this story began, none of it registers on a timescale where mountain ranges rise and fall like passing weather, where entire climate regimes shift and stabilize across spans of time too long for any single mind to hold onto directly. That is not a reason to dismiss the present moment. It is simply a reminder that the present moment, however weighty it can feel from the inside, is also, always, a small and passing thing, held gently within something enormously larger, older, and more patient than itself. A finished story wraps its loose ends neatly together and sets them aside. An honest story, especially one built from evidence still actively being gathered, does something different. It leaves certain threads visibly, deliberately unresolved, not from any failure of effort, but because that is simply the current, honest state of human knowledge on the matter. There is a kind of peace to be found in that honesty, the same kind of peace found in a piece of music left deliberately unresolved, its final chord held softly rather than firmly closed, inviting quiet stillness, rather than demanding an ending. What remains, now, is simply the knowledge itself, freshly won, still incomplete, and, in its own unfinished way, a genuinely honest gift. The plain fact that this small, quiet corner of the galaxy has a far richer, far stranger history than anyone assumed even a few years ago, and that a good portion of that history is only now, for the first time, becoming possible to read. That is where this particular story rests for now, not with an answer, but with a far better question than anyone had access to only a few short years ago, drifting quietly alongside a solar system that, as it always has, and as it always will, simply keeps moving forward through the dark. Drift now, quietly, the way our small world once drifted through the stars.